Let's study radioactivity. Before we go into the details of the radioactivity, first of all, let us see that how the structure of nucleus has changed over time. Initially, in very early days, atoms were thought to be indivisible. It was the discovery of the radioactivity which led us to understand the atoms that they have a central nucleus. Then came up a scientist whose name was Rutherford, and he proposed us a planetary model in which, just like planets, electrons were orbiting around a nucleus. Then came the nuclear force in 1930s. That was the time when the strong nuclear force was discovered. Remember that strong nuclear force is the force which holds protons and neutrons together. Then came up the shell model in 1940s, in which we saw the development of the nuclear shell model that actually explained us the nucleon arrangement. Then came the liquid drop model, and it described us a little bit about the nuclear behavior. And then came up the quark model in 1960s, which gave us the building blocks of protons and neutrons, which are the quarks. And then in 1970s, we got a standard model of particle physics, which were explaining us the quarks and the forces. And our more modern understanding today of the nucleus is that it comprises of protons and neutrons, and these protons and neutrons are made up of quarks, and they are held together by strong nuclear force. So apart from all these early development, you should first of all remember two things that are really important. The quark model, that our protons and neutrons are made up of different types of the quarks, and that you should understand that there is a strong nuclear force. You should understand that unstable nuclei will always emit three types of radiations. Either it could be an alpha radiation, either it could be a beta radiation, or it could be a gamma radiation. Now, let us study them one by one in detail. First one is alpha particles. Alpha particles are actually helium nuclei, and these are made up of two protons and two neutrons. And this is the structure of helium. Helium is what? It is an atom or an element which is made up of two protons and two neutrons. And they are very strongly ionizing, and therefore they can travel a few centimeters, and they are actually stopped by a thick piece of paper. And they are slightly deflected by strong magnetic and electric fields. Now, these features which I have just mentioned, you need to learn them for your final board exam, and especially for the physics of radioactivity. You should actually know these characteristics of the alpha particles. I repeat it again for you. They travel a few centimeters, stopped by a thick piece of paper, detected slightly by a strong magnetic and electric field. Then comes the beta particles. What are beta particles? Beta particles are fast-moving electrons. Unlike alpha particles, they are deflected through large angle by electric and magnetic fields. They travel several meters in air, and they are absorbed by aluminium, which is few millimeters thick. So remember these features about the beta particles. They are absorbed by aluminium, which is few millimeters thick, and they travel several meters in air. Then comes the gamma particles. Gamma particles are electrically neutral. Why? Because these are the photons. Because they are the photons, they are not deflected by electric or magnetic fields. Definitely why? Because photons are not charged particles. They are very weakly ionizing, and their intensity is actually reduced by few centimeter thickness of lead. For gamma radiation, remember that it behaves like any other electromagnetic radiation. It spreads out symmetrically in all directions from its source. And therefore, it obeys the inverse square law. So gamma radiation can be written as inverse square law. What is the inverse square law? It states that the intensity of radiation is inversely proportional to the square of distance from the source. And in this equation here, which is in front of you, I is equal to k over x square. K is a constant. The units for the intensity come up to be Webers per meter square. Then let us know what does it mean by background radiations. On our earth we have a lot of rocks, like for example uranium, thorium, radon and potassium. So definitely we are always exposed to some ionizing particles. Radon is a gas that emits alpha particles. And because we inhale these gases, and radon is a dangerous radiation, and like many other radiations in the air, it can go inside our lungs. In addition to this one, the sun is actually emitting lots of protons, which can also create ions in our atmosphere. These are the two sources. Which are the two sources? First are some ionizing particles and gases, and the other thing is the sun's emission of lot of protons, which is causing ionization. So this is the figure 6 here, which shows you the total contribution to this background radiation from all the places in the Britain. So you can see most of the ionizing radiation is coming from the cosmic rays and radioactivity in the air, but there are some coming up from the medical fields and foods as well, and the rocks which are not under our control. Okay, now what are the risks and benefits of uses of radiation, especially in the medicine? Because in the medical field, we are using some X-rays, CT scans, MRI and PET scans, which are using these radiations for the purpose of diagnosis. By the help of these radiation therapy, we can treat cancer, and we can reduce the tumor size. We can actually relieve some symptoms. It also helps us to develop new treatments and medications. But the risk is that ionizing radiation, although they are treating the cancer, but still ionizing radiation increases the risk of cancer. And this is one of the very contradictory situation in the medicine, that the treatment which we are doing for the cancer is actually itself causing us the cancer. So especially when it is done in very high doses, or when it is done for the prolonged exposures, then these radiations might cause some genetic mutation which can lead to health issues, and especially some high doses can actually damage the tissues, can cause burns, and sometimes the organ dysfunction as well. So let us discuss the Einstein theory of relativity. So what does the Mr. Einstein told us? He told us that energy is equal to mc squared, where he said energy and masses are interchangeable. What did he told us? He said when something travels at the speed of light, it becomes an energy. And for that purpose, he gave us this equation, which is E is equal to mc squared, where stands for the mass in kg, c is the speed of light, and E is definitely what is the energy, which is given in joules. Let us now talk about the mass defect, or in other words, the binding energy. We just came to know from the Einstein's theory of relativity that masses and energy are interchangeable with each other. So therefore, if you want to separate a nucleus into its nucleons, we must provide it with a energy, and that energy is called as the binding energy. Binding energy is actually the energy that would have to be supplied to the nucleus in order to separate it into constituents. And most of the time this is measured in joules or sometimes in mega electron volts. If I want to explain you the concept of binding energy, I would say that it is the energy that corresponds to the mass defect. What is the mass defect? Mass defect is if you measure separate nucleons mass and the nucleus mass, there is a difference in the mass. Why? Because the energy that we have supplied in order to separate that nucleus has also converted to mass in the nucleons which are separated. So that is called as the mass effect. Now let's talk about a unit which is called as atomic mass unit. Atomic mass unit is the unit of mass and it is used to express the mass of atoms and molecules. Or we can say that one atomic mass unit is equal to 1/12 of the mass of carbon. And one atomic mass unit is almost equal to 1.66 times 10 raised to power minus 27 kg. Now, why are we using this atomic mass unit? Because definitely it's very easy to express the mass of the atoms and molecules. It's very convenient and it's very easily understandable. Okay, so the table 1 that is given below here, you can see here they have given us the masses, or you can say the atomic mass unit and the masses in kg, and they are given in a large number of significant figure because the differences are very small for the protons, neutrons, and helium nuclei. You can see this very carefully because you might need this in the few calculations for the exams. Now, there is a very typical question coming up in the A-level exams. They ask you to calculate the mass effect and binding energy for oxygen molecules. So, listen, for an oxygen molecule, what is the data they have given us? They have given us the mass of the oxygen nucleus, which is almost equal to 15.9949 atomic mass unit. Then the mass of the proton, as per our data, in the last slide you have seen in the table 1, they have given this. It's the mass of the proton is 1.00728 atomic mass unit. Mass of neutron is 1.00867 atomic mass unit. Number of protons are 8, number of neutrons are 8. So first of all, we should add up the separate nucleons and find the mass, and then we will subtract that from the nucleus. So therefore 8 protons and 1 mass of the proton is 1.00728. So 8 times 1.00728 plus 8 times 1.00867, and I'll subtract to 15.9949 from this. And at the end, I have a mass effect of about 0.1327 atomic mass unit. But since I have to express in mega electron volts, one atomic mass unit is equal to 931.5 mega electron volt. So therefore, I will multiply 0.1327 by 931.5 mega electron volt, and I will end up with the binding energy, which is equal to 123.6 mega electron volt. I came to know that this one atomic mass unit is equal to 931.5 mega electron volts. Energy is equal to mc squared. Mass is equal to for one nucleon is equal to 1.66 times 10 raised to power minus 27, and speed of light is it's 3 times 10 raised to power 8. I do this one and I end up with an energy of about 1.49 times 10 raised to power minus 10 joules. And this is how much the energy is for one in joules. So 1 mega electron volts, it is equal to 1.6 times 10 raised to power minus 13 joules. I'll divide it by 1, this one, and I end up with energy which is almost equal to 931.25 mega electron volts. They do not ask this derivation or to show this very much in the exam, but anyhow, you should at least have the idea about this one. So in order to find out the binding energy per nucleon, you will divide the total binding energy by the number of nucleons. Also remember, the binding energy is different for different nuclei, and the average binding energy per nucleon is equal to total binding energy over number of nucleons. Thank you so much. We'll end up here with our topic related to radioactivity. It's not finished yet. Please follow the other playlist for further lessons. Thank you so much.
Tutoring and resources, log on to www.physicsonlinetuition.com.